this lecture, I will show you the behavior of capacitor C in RLC series circuit. Let's find the voltage response of a capacitor when switch is closed at t equals 0 in figure 1. Applying KVL to the circuit, but all initial conditions are 0, Ri, voltage drop of a resistor, a reactance, and the capacitance. Since current I through the capacitor is C dVc dt, equation 1 becomes RC dVc dt plus LC dVc square dt square plus Vc equal V. To find the natural response, set the force function is 0. First function is 0, and then the characteristics is set by like this: S square plus R over L S plus 1 over LC equals 0. The roots of characteristic equations are S equals minus R over 2L plus minus root R over EL square minus 1 over root 2 LC square. Then we set minus alpha plus minus root alpha square minus omega 0 square. Alpha is damping coefficient, omega 0 angular resonant frequency. The general solutions of the voltage response of capacitor in RLC series circuit can be divided by 3 types depending on the roots of characteristic equation. Here are 3 general solutions type. First, overdamped case. Voltage response type is Vnt equals K1 exponents S1t plus S2 exponents S2t. S1 and S2 are roots of characteristics. Second, underdamped case, voltage response Vnt equals exponential minus alpha t a cos omega dt plus b sin omega dt, where omega d is root omega 0 square minus alpha square with a natural resonance frequency. Third, critical damped case, voltage response Vnt equals K1 exponents minus alpha t plus K2 t exponents minus alpha t. We want a complete solution with the first function and then equals natural response Vnt plus first response Vft. The first item is the right side in the natural response, and the second item is the same as the first function, value in response to time t approaches infinite. That is, all of the voltage is applied to the capacitor. I am talking about response of second order differential equations in RLC circuit. This is a simple RLC circuit in series connection. The C equals 0.1 microfarad, L equals 10 millihenry, internal resistance 33 ohms. R is a variable resistance because I chose R1 100 ohms, R2 200 ohms, R3 600 ohms. And the power supply, applied voltage, you get the 2 volts. When I calculate alpha 1 and omega 0, and then alpha 1 is greater than omega 0, and R2, same manner, alpha 2 is greater than omega 0, and R3 equals 600 ohms. Alpha 3 is almost same to omega 0. I think case R1 is underdamped, R2 also underdamped, R3 case critical damped. I'll show you the experiment response of the capacitor. Here is capacitor 0.1 microfarad, choke coil or inductor, 10 milliamps, and here is several resistors, and 100 ohms, 100 ohms, 300 ohms, 300 ohms. And when I chose the 100 ohms, the total resistance 133 ohms, and then the response of a capacitor voltage like this. It has overshooting like this. And then I chose the 200 ohms. Overshooting is smaller than before. And the last, R3 equals 600 ohms. If the case critical damped. Like this. This graph is almost the same the RLC circuit, the response of a capacitor, charging capacitor. Okay. When I simulate this circuit with the MATLAB, first R1 is 133 ohms, and then like this, R2 233 ohms. It also has overshootings, but smaller than case A. And the C, R3 equals 633 ohms, and then it has the same as the only RC circuit charging voltage. To summarize this lecture, I'll show you the comparison of experiments and the MATLAB simulation. Upper figures made by experiment, lower figures by MATLAB. First, under-damping case. It has several overshoot here, and then the final, it has 2 volt voltage across the capacitor. And then when I simulate it also, it has several overshooting, and V equals 2 volt. This figure current through the capacitor. Here is oscillations, and it is a zero current. B, under damping case, also it has overshoot here, here, and the current ICT also has oscillation, is smaller than before, but it has oscillations, and then current approaches 0. Last, critical damping, there is no overshooting, just like this, but the current also no oscillations, just like RC series circuit.